Hi, so today I'm going to talk a little bit more about what the strong acids and strong bases are and how they neutralize each other, and then we're going to look at titration. So first of all, what are the six strong acids? HCl, HBr, HI, HNO3, H2SO4, and HClO4. And we just did naming, so can you name those? I'll let you think for a minute. So remember with the naming that if it just has two elements, then that's when you use the prefix hydro, and then you change the ending on the second element to ic. So HCl is hydrochloric, and then you add acid on the end. So hydrochloric acid. HBr would be hydrobromic acid. HI would be hydroiodic acid. Now, the other three strong acids are not just two elements, they are with the polyatomic ions. So for those, you had to know the name of the polyatomic ion, and then adic-itis is the rule. If the polyatomic ion ended in ate, then it becomes ic as an acid. If it ended in ite, then it becomes us as an acid. So HNO3, that was nitrate. So that's nitric acid. You don't use hydro because there's a polyatomic ion. Well, hydro is only with when there's just two elements. So then H2SO4, SO4 is sulfate. So 8 becomes ic, but it's not sulfic, it's sulfuric. And that's just what you have to remember. That's the way it is. So sulfuric. So it's still the 8 became ic, but it's sulfuric acid. And then the ClO4 is the chlorate. It's perchlorate. So that would be perchloric acid. And those are all written there for you. Okay, so those are the six strong acids. That means every other acid is a weak acid. So any other acid you've heard of, citric acid, boric acid, many other acids, those are weak acids. Okay, so with our strong bases, those would be the alkaline metals with hydroxide or alkaline earth metals with hydroxide. And those strong bases completely dissociate in water so that we can get the OH minus concentration, OH minus from the concentration of the base. So they have a alkaline metal like NaLiK with OH, or an alkaline earth metal, the bigger ones like Ca, Sr, with the OH, and those are your strong bases. Okay. Strong acids and bases completely dissociate in water. They break apart in water. So if you have 6 molar NaOH, when it breaks apart, you get 6 molar OH minus. If you have 1 molar HCl, when it breaks apart, you get 1 molar of the H3O plus from it. So that's why you can easily figure out the pH of strong acids and bases, but not weak acids and bases. With weak acids and bases, it's not easy to determine their OH minus or H3O plus concentration because they only partly dissociate in water. They actually set up an equilibrium where they start to dissociate, but then these ions can get back together and go back that way. So if it's 1 molar HF, it is not 1 molar H3O plus coming off. If it is 1 molar of the weak base, it is not 1 molar for the OH minus. So we're only going to calculate the pH of strong acids and bases, and today we're going to titrate with strong acids and bases. We're not going to worry about the weak acids and bases right now. Okay, so what do you get when you mix an acid and base? Well, if you mix HCl and NaOH, the H from the acid combines with the OH from the base, so you get HOH, which is water, and then the Na goes with the Cl, so you get NaCl. And with the sulfuric acid, again, the H would combine with the OH of the magnesium hydroxide, and you would get HOH, which is, again, water. And this time you're going to get two waters because you have two OHs coming off and two H's coming off. And then the other two combine, and you get MgSO4, which is your salt. So you always get, when you mix a strong acid with a strong base, you get water and a salt. That's just the generic term for an ionic compound. Okay, so the H combines with the OH from the base, and you get water and a salt. So these are called neutralization reactions or acid-base reactions. So a joke, did someone mix your acid with a base because you're a bit salty today? Another joke, why does the military stockpile hydrochloric acid? To neutralize the enemy's strongest bases. All right, so next I want to talk about titration. And titration is when you're taking a solution that you know the concentration of, and you add it to a solution that you don't know the concentration of to calculate that concentration. We're going to do acid-base titration. You also could do some other kinds of titration, but we're going to just do acid-base. So we're either going to know the concentration of the base and use it to find the concentration of an acid, or vice versa. We'll know the concentration of the acid and use it to find the concentration of the base. So the important thing to note about titration is you have what's called the equivalence point. That's where the moles of H plus from the acid exactly equal the moles of OH minus from the base. So those have come together to make water at the equivalence point. And we'll talk in a minute about endpoint, where you can see a color change. Okay, but equivalence point, if we were measuring with a pH meter that measures the pH, we would, let's say we started with an acid. So the pH would be low, remember, under 7 if it's acid. And then as we add base, add base, add base, when we've added exactly the amount of moles of OH minus from the base that we have of H plus from the acid, that would be water, and the pH would be 7. So at the equivalence point, the pH is 7. We can, instead of trying to measure the pH with a pH meter, we can use what's called an indicator. And indicators are used for estimating pH. An acid-base indicator is a weak organic acid that actually changes color. So it's a different color when it's an acid than it is as a base. So when we use that in a titration, if we put it in the acid, it'll be one color. And then as we add base, 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 when the acid-base indicator gets converted to its conjugate base, the color will change. And so in titration, the endpoint is going to be the point where the indicator changes color. So we don't have to actually measure the pH. We're looking for the color change. And different indicators change color at different pHs. We're going to use phenolphthalein, which is colorless in pH below 7, acid, and then it turns pink when the pH is at 8. So this is going to be very close to the equivalence point because it will take like one drop of the base to jump up from an acidic pH when it's really close to the equivalence point to a basic pH. Okay, so the endpoint for us is what we're going to look for in the titration, and we'll be really close to the equivalence point where the amount of acid is equal to the amount of base. If we were actually doing this in lab, which you would be doing it in lab if we were in class, And I'm going to demonstrate titration for you in the next session. But we use what's called a burette to accurately measure volume, the big, tall glass burettes. And when whatever you have up in the burette is called the titrant, and the little valve that you turn to slowly let, or you can do it quickly, depending on how careful you're being. This turns, it opens to let the liquid in. That's called a stopcock that you turn. And then what you're analyzing down below is the analyte. So this is a real picture of what it looks like. If you had your acid to start with, it would be clear. You put the phenolphthalein indicator in there, it would be clear to start down here. And then the base would be up here. So if we have an unknown acid and we're using a base to titrate it, as we add base, it will just barely start turning pink. You keep swirling it until it stays pink. And then you measure how much volume it took of the base to neutralize that acid, which we'll know when it turns light pink. Okay. If we were measuring the pH, we would start off, this is called a pH a titration curve, when you're graphing pH versus how much titrant you've added. If we started with an acid, the pH would be low, below 7, and we start adding base. At first, we have a lot more acids, so the pH would barely go up, barely go up, barely go up as we're adding base, adding base, adding base. All of a sudden, when we are almost to the equivalence point, we'll get a big jump in pH if we were measuring the actual pH. And right smack in the middle of that jump is the equivalence point, pH 7. So it's impossible to actually get to stop right at where the equivalence point is, because one drop takes it from acidic pH to basic pH. So that's why we graph it. And then we know right in the middle of that is the equivalence point. And so we would be keeping track of how many milliliters of NaOH we added if we were doing NaOH with HCl. And then right here, we could come down and see how much NaOH it took to neutralize our acid, because we would know that by the equivalence point. That would be if we were graphing. But we're not going to graph these. We're just going to see how much base it takes to change our acid from clear to pink, because then we'll know that we've neutralized our acid. So our titration problems that we're going to do, we're going to use a strong base to calculate the concentration of a strong acid, or a strong acid to calculate the concentration of a strong base. The main idea, we have to remember the molarity equation. Molarity is moles over liters. So if we multiply molarity times the volume in liters, that will give us moles. And then at the equivalence point, the moles of H3O plus from the acid equals the moles of OH minus from the base. Okay, and then at the end, I'll show you there's a little shortcut equation, MAV equals MBVB. Okay, but first we're going to look at it from the mole standpoint. Okay, so problem 1. What is a molarity of an HCl solution if 28.6 milliliters of 0.175 molar NaOH is needed to neutralize a 25 milliliter sample of HCl? So back to that picture, down in the flask, I would have 25 milliliters of HCl. I would put a couple drops of the indicator, that's all I need. And then I would have up in the burette the NaOH, that's 0.175 molar. And so I would add the NaOH, and it took 28.6 milliliters in this problem to make it turn pale pink. Again, I will show you an actual titration tomorrow. But just calculation-wise, then we know the molarity of the base and we know the volume of the base, so we can calculate how many moles of base we had to add. So 0.175 is the molarity. We need to put that volume of base into liters, so divide by 1,000, move the decimal 3 places. So it's 0.0286 liters, and we're solving for moles. So 0.0286 times 0.175 gives us the moles of NaOH that we added. And now looking at the balanced equation, it's a 1-to-1 ratio. So it takes just as many moles of NaOH as we had moles of HCl to neutralize. So that means if there's 0.00501 moles of NaOH when it was neutralized, there's also 0.00501 moles of HCl. They're equal to each other. And so that's how much reacted. So then we can calculate the molarity of the HCl by dividing that moles that we just found by how much HCl we had, which it told us in the problem that there was 25 mils of it. So putting that into liters is 0.025. So dividing moles by liters, we get the molarity of the HCl, which is 0.200 molar. Okay, let's try one more. A 25 milliliter sample of HCl is placed in a flask with a few drops of phenolphthalein and very similar type of problem. 32.6 mils of a 0.185 molar NaOH solution is needed. What's the concentration of the HCl? Okay, so once again, when we multiply the molarity times the liters, that gives us moles. So the molarity of the NaOH times the liters, moving the decimal 3 places, 0.0326 liters gives us moles of NaOH. And incidentally, since there's one OH in NaOH, that's also the moles of OH minus. And then because this is the equivalence point, or the end point, which is close to the equivalence point, we know that that's also the moles of H plus. And because there's one H plus in HCl, we know that's the moles of HCl. Okay, so we use the moles of NaOH. It's all 1-to-1. So that gives us the moles of HCl. So now to find molarity of HCl, I plug in the moles. I divide by the volume of HCl in liters, which again, it was 25 milliliters. So 0.025 liters. And when I divide those, I get my molarity, 0.241. Okay. And so then lastly, this shortcut equation works as long as the acid is like HCl, HNO3, HBr. If the acid only has one H in it, and if the base only has one OH in it. So if it's like NaOH, KOH, any of the alkali metals with OH. If that's true, then we can use the shortcut, MAVA equals MBVB. So for that problem I just did, we know the molarity of the base, 0.185. We know the volume of the base, 32.6. We know the volume of the acid, it's 25. What we're solving for is the molarity of the acid. So molarity of the acid equals 0.185 times 32.6 divided by 25, and I come up with 0.241. So it's exactly the same whether or not I use this equation or whether I calculated moles and then divided the moles by the liters of acid. Both cases, I come up with the molarity of my acid, 0.241. Okay, so we're going to stop there for today and then do some problems on this acid-base stuff. And then tomorrow I will show you actual titration experiment.